And okay, so the string is unusual in that it has an operator, right? So it's the only class that has it has a redefined addition operator. Sorry, just a second here. Okay, there we go. It's the only class that has a redefined addition operator, right? So for strings, joining the addition operator is the concatenation operator, which lets you join the characters of two strings to create a new string, right? So that's the important part, right? It doesn't add it doesn't change one of the two strings, right? It creates a third. If you add two strings together, it creates a third string. Right, so if you wanted to make the string James Bond 007, you could just write it down like that, right? Or you could concatenate three strings together, right? So James with a space, and then Bond with a space, and then 007 at the end. If you test if those two strings are equal using the equals method, right, you'll get true. You can concatenate primitive values onto a string, right? So same example as before. I'm going to make a new string this time. This time concatenating 0, 0, and 7 onto the end of the string. This also works. Right? So if you start out with the string James Bond, then you can join anything to the end of that string. Right? So in Java, you can join primitive values to the end of a string, or you can join other object references to the end of a string. And Java will automatically do the sensible thing or the expected thing when it concatenates objects onto strings. So what happens if you concatenate an object onto a string is that Java will automatically call the toString method on your object here, and then concatenate the string with the string in front. You have to be careful about the order of operations when you do this, though. Right. So here I'm going to try to make the string ha ha, but I'm going to start with two cars, right? The car H and the car A. When Java sees an expression like this, all it sees is something plus something and something plus something. So it says, well, everything just involves addition, and addition has the same precedence. So I'm going to compute the expression from left to right. So computing the expression left to right, Java sees a car and a car. Right? So Java uses int arithmetic to compute the sum, which turns out to be 201. It then sees an int plus a string. So now it uses string concatenation and joins the ha to the end of 201. And so you end up with 201 ha instead of ha ha. Okay, so the explanation is repeated down here. You can do other things as well. So you can get unexpected results by even if you have a string in the front. Right. So if you have a string in the front, and then somewhere else you've got a pair of parentheses. Right. So you've got a string concatenate with something, but the something's in parentheses. Right. Then whatever is in the parentheses happens first. So if you concatenate two types, so if you use the addition operator with two things in parentheses, then Java might not perform string concatenation with the things in parentheses. So you have to be a little bit careful about that. There's a notebook that gives you a bunch of that gives you several other examples of when string concatenation can go wrong. Slicing strings. Slicing strings in Python, you just use the square brackets, right, and the index with the colon. Right. So 1: means slice or give me the part of the string S starting from the second character going to the end of the string. Right. So you get B, C, D, E, F, G. Right. 3:4 means start at the character at index 3. Right. Go up to but do not include the character at index 4. Right. So you always have to remember that when you're slicing, it never includes the character at the last index. Right. So that gives you the character D. So when you slice using 5 through 7, that gives you back the characters at index 5 and 6, right, which is FG. Java's substring method does more or less the same thing as the Python slice. So you can use the exact same indices with Substring as you do when you compute the slice in Python. So for Python programmers, Substring is or should be relatively straightforward to understand. Now, unlike Python, you cannot use negative indexes, right? So you're not allowed to use negative indexes at all in Java. So whenever you are using a class that requires an index or an array, right, that uses an index, you have to remember there's no negative indexing, right? If you want to get in, if you want something from the back of the collection, you have to use the appropriate positive index, which is a little inconvenient, but that's just the way it works in Java. What else do I want to say about? Oh, I wanted to say, so even in second year, so even in CISC 220, there are still students who are trying to slice things in like a completely different language. So they're trying to slice things in C with a negative index. Negative indexes only work in like in Python and some other languages, some other newer languages as well. They don't work in languages like C and Java. Python also allows you to redefine how operators work for your classes. Right? So Python also has classes. String in Python, str is the string class in Python. Right? So you're allowed to, the creator of the class is allowed to redefine how operators work for a Python class. At least some of them anyway. I don't know if we can redefine all of them, but you can certainly redefine some of them. So you can certainly redefine less than, greater than, equals, equals, and things like that. So in Python, less than and greater than with strings compare strings in lexicographical order, right? So dictionary order, right? So is s less than t asks, does the string s come before the string t in the dictionary? And the answer is yes, right? A comes before z, right? The string s greater than t asks, does string s come after t, right? So that's no, right? Equals equals is the equality operator in Python. So it's logical equality when you use classes in Python. Right, so that gives you true. Remember in Java, you want to use dot equals here. You don't want to use equals equals. Compare to is the method that you use if, number one, if the class defines it, that's the method that you use. And it's the method that you use when you want to check, you want to compare two objects somehow, right? Now, exactly how the objects are compared depends on the definition of compare to for that class, right? So for example, if you compare two date objects in Java, right, then compare to works by comparing by looking at the actual dates of the two objects and determining which date comes before the other date. Right. So for two strings, the compare to method, when you look at its documentation, says it compares the strings in their dictionary order. Right. So s compared to t. Right. Now, compare to doesn't return a Boolean like it does in Python. So compare to returns an int in Java. Right. So s compared to t returns an integer value that's less than 0, so some negative value if s comes before t. S compared to returns 0 if they compare as equals, right? So for strings, compare to returns 0 if s equals t happens to be true. This is not the case for every class, right? It's possible to compare two objects belonging to some class and compare to return 0, but equals does not return true. We'll look at examples of that when we implement the equals method. S compared to t returns a positive value if s comes after t in the dictionary. If you look at the documentation, it will tell you what the actual value that's returned, what it corresponds to. Sometimes it carries information with it, sometimes it doesn't. So for many classes, compare to will just return -1, 0, or 1. Right? So all that the general contract for compare to says is that it returns a negative value if s comes before t. It returns 0 if s and t compare as equal. It returns a positive value if s comes after t, right? Where before and after depend on the class that you're using. So for strings, everything's done in dictionary order, right? So if I compare aardvark to zebra, right? So s compared to t, that's going to return a negative value because aardvark comes before zebra in the dictionary. If I compare s to itself, right? So s compared to s, that always returns 0, right? T compared to s, so if I compare zebra to aardvark, that should return a positive value because zebra comes after aardvark in the dictionary. Okay. So when using compare to, there's a few things to remember, right? It's roughly the analog of less than and greater than, and equals to for objects. Right? It might not be defined for the class that you're using. Oh, I should tell you how you can tell. Do I have the string documentation anywhere? Off here so you can't see my mail. Here. Okay, so when we look at the documentation for string, the way you can tell that it defines compare to is right here. So at the top of the class, where you see the name of the class, you'll see a section that says all implemented interfaces, right? If you see that it implements comparable, then you know that there's a compare to method. We're going to look at interfaces later on in the course. Similarly, if you just scroll through to the method section, you can find the compare to method here. Right? And you can see that the summary says that it compares two strings lexicographically, which just means in dictionary order. Right. Some other methods. So there's a lot of methods in the string class. We've looked at several of them now. The last one I want to look at is called replace. So replace is one of these methods that will either accept a pair of char, right, or a pair of strings. So there's two different versions of replace for the string class. If you give it a pair of char, then it will replace every occurrence of the first character with the second character. My string s, which points to sparring with a purple porpoise, right? If I replace every p with a t, then I get starring with a turtle tortoise, right? So the string t will be equal to that string there. Here I've got the string hi ho, it's off to work we go. Right? If I replace hi ho with oh no, then every occurrence of hi ho gets replaced with oh no. Right? So oh no, it's off to work we go. The strings don't have to be the same length. So the length of that can be different than the length of that. Right? So replace does pretty much what you expect, what you think it would do. Right. So that's the end of the string. Right. At some point, it would be useful, right, to you if you went into the string class documentation and scrolled through it and look at what it can do. Right, because there's lots and lots of methods. Anything that deals with a code point, you don't have to worry about because that deals with Unicode. So you won't be able to figure out what code point, any method that involves a code point does without knowing what the Unicode standard is. And so for our purposes, that's not really that important. But there's lots of methods here, and it's in order to use the class well, you need to be aware of what methods the class provides. Right. Otherwise, you end up writing code when you don't have to. Right. So you might want to do something like, well, for example, if you wanted to find the location of a character in a string, right, and you didn't know that the index of exists, then you'd end up writing your own loop every time, which is silly. The string class is designed to provide it's designed to provide many commonly used operations, right? That's the point of creating a class or creating a type in Java. All right, so that's it for strings. We're now going to move on to floating point. So this is a bit of a so the course description says that we have to do this. So if you read the calendar description, it says that we have to do some our students need to be introduced to how numbers are represented on a computer. So floating point numbers in particular are a bit odd. Now, you know from Python, right? Python has floating point numbers, right? So the class in Python that represents a floating point number is called float. Now, the Python float is the Java double. So that's the, which is confusing, right? Because Java also has float. Why Python chose float for its name, I don't know. Because the Python float is what's called a double precision floating point number. I don't know why they chose float instead of double. That's very confusing. But anyway, these approximate real numbers in Java. Right? Now, why do I say approximate? Because real numbers in mathematics, real numbers, when you write them in any base, might have an arbitrary number of digits. Right? So you can have a real number that has an infinite number of digits. Can't represent an infinite number of digits on a computer because every computer has finite memory. Right? So float and double, these occupy fixed and finite amounts of memory. Right? Float's 32-bit, double is 64-bit. And so that has certain implications. Right? One of the, so I guess the main implication that we want to talk about today is that there are numbers that you can write down in decimal, right, base 10, that that you can't represent exactly on your computer, and the results are very unintuitive. So, for example, if I compute 0.1 plus 0.1 plus 0.1, everybody here knows that's 0.3. Okay. But if you ask Java or C or Python, is x equal to 0.3? The answer will be no. So when you print, if you actually print out EQ, you'll get false, right? Which is very strange. Right? The reason this happens is because you can't represent 0.1 exactly using the representation of double that the language says is used. You also can't write. You also can't represent 0.3 exactly either. So here I've got a program. I think, do I still, hopefully I still have it up. It'd be nice if I did. Oh, I don't have it up anymore. Hang on. I just have to pull it up. All right, so while that reloads, let's go over this program. Just wait for Eclipse to go away, please. Well, that's inconvenient. Oh, there we go. Okay. So here I'm going to compute 0.1 plus 0.1 plus 0.1, right? I'm going to compare it to 0.3. I'm going to print out the result. And then I'm going to print out a bunch of stuff that hopefully explains why this happens. So I'm going to take 0.1 and I'm going to pass it to this method called allDigits. Right? AllDigits uses this class called big decimal. In Java, this is the class that lets you represent arbitrary precision floating point numbers. So arbitrary precision means that you can have as many decimals, as many digits in the number as you have memory on your computer. So that class is defined, you import it like this, right? So it's defined in the package java.math. It's using the class is kind of beyond the scope of this lecture, right? So explaining how it works and everything that it can do, that's not really important right now. What I want to do is I want to take that double value, pass it into big decimal, right? And then I want to ask big decimal to give me back, to give for the string representation of that value. Okay. So I'm going to ask for the string representation of 0.1, right? The big decimal string representation of 0.1, right? So not the double representation of 0.1, right? Then I'm going to do the same thing for 0.1 plus 0.1, and then 0.1 plus 0.1 plus 0.1, and so on and so forth, right? And then finally, I'm going to do the same thing for 0.3. Right, so if I have, if everything, no, that's the wrong thing. Oops. Yep, perfect. All right, so there's our program. If we run our program, following. Sorry, so I forgot to change the font in the console. So that's going to be hard for you to read, I think. Okay, but so I'll just read out what it prints. Right? So for EQ, it prints false. Right? So in fact, 0.1 plus 0.1 plus 0.1 is not equal to 0.3 according to Java. Right? Now, why is that the case? So if I print out what 0.1 is, or what Java thinks, or what big decimal thinks 0.1 is, right? This is what gets printed out. Right? 0.1 and then a bunch of zeros and then a 5 eventually, right? And a whole bunch of digits down here. Right? So it's not exactly equal to 0.1, it's equal to 0.1 and a little bit. Right? So if you add them together, right, you're going to get 0.3 and a little bit, probably. Right? That's probably what you're going to get. And in fact, you can, that's true. You can confirm that's true by looking at the output of line 17. Right. So line 17 says that the sum of 0.1 plus 0.1 and 0.1 is 0.3 and a little bit. So there's a 4 over here. If you add 4 0.1s, you get 0.4 and a little bit. Right. Now, the weird part here is, so if you think about this, right? So every time I add so 0.1 apparently is 0.1 apparently on the computer is slightly bigger than 0.1, right? So if I add 0.1 5 times, you would think that you get a number that's 0.5 and a little bit. But in fact, you don't. You get back 0.5 exactly. So that's extra confusing. Right? Now, what about 0.3, right? So if I sum them together, right, I get 0.3 and a little bit. But if I ask Java or big decimal, what do you think 0.3 is? You actually get a number that's slightly less than 0.3, right? You get 0.299999999 something. So all of this is very strange. This slide is, the output of that program is actually slightly misleading. Right? So what you should not take away from that, from the output of that program, right, is that double has a whole bunch of decimal points, right? So that's not what you should take away from this, right? So do not think that double has like I don't know, what's that, 32 or 64 digits after the decimal point, right? It does not. Okay, so a double has roughly 15 to 17 significant digits when expressed in base 10. I'm going to explain why that happens in a second. Right. So the program prints out much more than 17 digits. Right. So what's going on in this program? Right. So what's happening is we're taking the literal 0.1. Right. So that's my double literal. Right. Now the computer can't represent 0.1 exactly. Right. Furthermore, the computer is using base 2. It's not using base 10 to represent this number. Right. So it takes the base 10 number and converts it to the closest possible base 2 number. Right. Exactly what that is not important for our purposes, right? But it converts it to the closest possible base 2 number, right? And then, right? And then when I pass that number, right, 0.1, right? So remember, internally Java is going to take this 0.1, convert it to its base 2 representation, right? That's not exactly equal to 0.1. And then you're going to pass it to big decimal, right? And big decimal is going to print out the string representation of that number, right? So the string representation of the binary, value, sorry, wrong slide. Where do we go? Right. So big decimal is going to return the string that corresponds to this base 2 number, right? The program is printing out the result of converting that base 2 number back to base 10. Right, and so when it does that, big decimal has an arbitrary number of digits. So I think it has, I don't remember what the actual number of digits it uses here. I think it might be 64, but I can't remember. You have to look at the documentation for the class. So what it's printing out is the result of converting the base 2 number back to base 10. Right, and because big decimal has more digits than double, you get a longer string on the output. Right, so remember for double, you have roughly 15 to 17 significant digits when you're thinking in base 10. Okay, so the representation that Java and Python and C and most other languages that use floating point, um, the standard that's used is something called the IEEE 754 standard. It is a very big standard that's well, it's very specific in how floating point arithmetic should work on a yeah. So it defines a particular way that floating point arithmetic should work. Right now, not every computer uses this standard. Right, so you can have some, in particular, you can have some inexpensive CPUs that may not fully support this standard. Right, but every desktop computer will have a hardware support for this standard. Now, the details of this standard are way beyond the scope of this course, and it's probably way beyond the scope of any undergraduate course. Right, the people who wrote this standard have PhDs in numerical computing. But what you need to know, or what you should know, is that so number one, internally the floating point numbers are represented in binary, right? So in base 2, right? So what that means is all your numbers are going to be something times 2, right, raised to some exponent, right? Because everything's in base 2. So every floating point number you can think of as being some integer s, right? That integer is allowed to be signed, right? So plus or minus. Some integer s times 2 raised to some integer power e. Right? So e and s are both integer values. Right? E is allowed to be signed, but you'll see how that's captured in a moment. So e, in fact, can be negative. Now, so once I've told you that, right? So once I've told you that s times every floating point number can be written as s times 2 to the e, right? From there, you can immediately prove that 0.1 cannot be represented exactly if s and e are integer. Right? So the proof is by contradiction. So I'm going to look for integer values s and e, right, such that s times 2 to the e is equal to 0.1. Right? Now, in this expression, right, remember s is an integer, e is an integer, right? Because the right-hand side is less than 1, you know that e must be negative. Right? So this has to be 1 over 2 to the something, right? Otherwise, there's no way you can get a value that's less than 1. Right? So e, we know from this expression, e is negative. All right, so let's start with that expression. Let's multiply both sides by 10 so that I get rid of the decimal, right? So I get rid of the decimal part of the number. So now I get 10s times 2 to the e, and that's equal to 1. Right? I can take 2 to the e, right? I can divide both sides by 2 to the power e. Right? So that gives me 10s equals 1 over 2 to the power e. Right? And I can bring the 2 to the e up to the numerator, right, by negating the e. Right? So I get 10s equals 2 to the minus e. Right? Now remember, e is already negative. So this is just positive. So this is just the absolute value of e. Right? And so what does that mean? It means the right-hand side is 2 times 2 times 2 times 2 times 2 e times. Right? Sorry, the absolute value of e times. Right? So there's just a bunch of 2's on the right-hand side. On the left-hand side, well, there's a 10. Right? What's the prime factorization of 10? Well, it's 2 times 5. Right? So there's a 5 on the left-hand side. There's all 2's on the right-hand side. Right? 5's prime. So you know that the prime factorization of the left-hand side is not equal to the prime factorization of the right-hand side. Okay. Therefore, there is no integer value s and e such that 10 times s is equal to 2 to the minus e. Right. So I can't actually write 0.1 exactly using this using the IEEE 754 representation of floating point numbers. Anybody have any questions about that proof? Okay. Okay. Float and double. Now there are 64-bit, 32 and 64-bit binary values. right? So I don't want to write 32 zeros and ones or 64 zero and ones all the time, right? It's too many digits to write down, and it's just going to be very confusing, right? Similarly, I don't want to work in binary because most people are not used to working in binary, right? So I'd rather work in base 10 for the purposes of this lecture, right? I'm going to define. Oops, does that mean that every value that could be produced from adding 0. No. So you saw that that program I ran. If you add 5 0.1s together, you actually get back 0.5 exactly. Right? Now 0.5, that's 1 over 2. So you can conclude right away that that has an exact binary representation, right? Because it's just 1 over 2. Right? So you know that E is -1 and the S is just 1. Right? So there you can in fact find, so it does in fact have an exact representation. Right? So when you add 5.1s together, you can in fact, you do in fact get back 0.5. And why can't you just say that 0.1 is 0.5 divided by 5? Because so I mean mathematically that's true, right? But when you divide 0.5 by 5, you get back 0.1, and 0.1 can't be written down exactly in binary. Now, if you're asking why can't you just store floating point numbers as rational values, right? Some integer divided by some other integer, right? That's a different question, and the answer is you can, but it's a lot more expensive computationally to do. You can in fact, right, create a class, create a Java class that represents floating point numbers as rational numbers. And some mathematical software actually does that, right? So Mathematica and Maple and what else? MATLAB, they all have the ability to represent real numbers as rational numbers, right? But it's much more computationally expensive to do so, right? And if you're writing a computer program that uses floating point values, there's a good probability that you want the calculation to happen very quickly. So you don't want to pay the price of using rational numbers. Right? So in other words, the extra precision that you might get by using rational numbers is usually not worth the computational cost. So that's the answer. For applications like banking, right? So monetary applications, they do go out of their way to use some other representation that doesn't that avoids some of the floating point issues. Okay, so I want a smaller. For the purposes of explaining how how floating point works, I want a smaller representation, right? I don't want 32 or 64 digit numbers, right? And I want to work in decimal. So I'm going to describe a decimal representation of floating point numbers, where there's only 4 digits available. Okay. Here's our representation. It's similar to the floating point one, right? So you have some integer number, right? And here I get 3 digits to write my integer number, right? I'm in base 10, so it's times 10, raised to some exponent, where the exponent is defined by a single digit, right? So we have 4 digits in total, 1, 2, 3, and 4. This is 0. This is 1 through 9, 0 through 9, 0 through 9, and that's 0 through 9, right? So my first digit's not allowed to be 0, right? Which means I can't have a number like 001 times 10 to the something, right? So our rule for today is going to be that digit D1 is not 0, right? So no leading zeros in the significand, right? In the number S. Now, our purposes today, I'm going to let the significand be signed, right? So I can let it be plus or minus. You have to remember that when you do this on a computer, so an actual hardware, you actually need to store whether or not it's plus or minus. In binary, I need a bit just to store whether or not the number is plus or minus. I'm going to ignore that today. Right? We will allow the significand to be signed without worrying about storage for the sign. For the exponent, I'm going to say that this digit here is always between 0 and 9. Right? Now I need to get negative exponents if I want to write numbers, positive numbers that are smaller than 1. Right? So to get the negative exponent, I'm going to take this digit and subtract 5. Right? And that lets the total exponent be somewhere between -5 and 4. So this is actually how it works in the IEEE format. This number here is called the bias. Right? So I have, right? So one more time, 3 digits, right? Always 3 digits here, right? That's never a 0. The exponent's between -5 and 4. Okay, now I can start writing down some numbers, right? So what's the smallest positive value that I can write down? Right? Okay, so the smallest positive value, so this exponent would be the most negative exponent I can have, right? So that's -5. Right? The smallest value I can write here is 100, right? Because the first digit's not allowed to be 0. Right? So the smallest positive value that I can have is 100 times 10 to the -5. I write that out in decimal at 0.00100. Now, so that's the smallest value. What's the second smallest value that I can write down, right? Or another way to put this, what is the next floating point number that's bigger than that? Right? Well, I can change the last 0 to a 1. Right? So that gives me 101 times 10 to the -5. So that gives me the decimal value 0.00101. What's the difference between these two values? Well, it's 0.00001, right? Or 10 to the -5. Right? So that's the spacing between adjacent floating point numbers when the exponent is -5. There's no way for me to write any number that's between these two numbers. So that's one of the implications of having a finite number of digits. Right? There's no way for me to write any floating point number that's between these two values. Now, what happens if I change the exponent? Right? So what happens if I go up to the next higher exponent? Right? Then the smallest number I can write with an exponent of -4 is 100 times 10 to the -4. Okay? So what's that decimal value? Well, that's 0.0100. Right? Now, the next largest value is 101 times 10 to the -4. Okay? So that's 0.0101. Right? Now, what's the difference between those? Well, that's 0.001. Right? Which is 10 times bigger than that. It's 10 times bigger than that. So now the spacing between floating point numbers, adjacent floating point numbers, right, is 1 times 10 to the -4. So the spacing between floating point numbers is not constant. It changes depending on the exponent, right? So for the int values, right, the spacing between adjacent int values is always 1. For floating point values, the spacing between adjacent floating point numbers depends on the exponent. Okay? If I use an exponent of 4, look at the spacing between values. The spacing between values is 10,000. Right? I cannot write any number that's between 1 million and 1,010,000. Yeah, 1,010,000. Right? Any number between these two numbers, right, either gets converted to that or it gets converted to that. There's no physical way to represent these numbers in our floating point format. Right? And that should be surprising to most people. Right? Furthermore, that difference, right, is way bigger than that difference there, right? It's orders of magnitude different. 9 orders, in fact, 9 orders of magnitude different. So those are the two things you should keep in mind, right? Spacing between floating point numbers changes, and it depends on the exponent, the value of the exponent. Right? Numbers that lie between, there are lots of floating point numbers that lie between adjacent floating point numbers. Okay, so that distance between adjacent floating point numbers, that's actually important for people who study numerical analysis, the science of computing values on a computer. Okay? So that distance between adjacent floating point values is called the ALP, right? It's the unit in the last place, right? Why is it called the unit in the last place? Because it's the difference here. The difference in the significand when both exponents have the same value, right? So that's a difference of 1 ALP. So the difference between adjacent floating point values is 1 ALP. The math class in Java will actually tell you what the value of ALP is for any floating point value. So if you ask what is the ALP for 0, it'll give you back some number, right? If you ask what is the ALP for 1 times for 0.01, you're going to get a different value, right? Because the exponent changes. Okay, so one source of error when you work in floating point is the fact that you cannot represent a lot of floating point numbers precisely, right? So I can't represent the number 1,000,001, for example, right? So if I want to do a calculation with 1,000,001, it's automatically going to be wrong because I can't even represent 1,000,001. Okay? So we need some way to talk about error. So if my true number, x hat, is 1,000,001, right? My closest floating point number is 1,000,000, right? Then the absolute error is defined as the difference between those. Okay? So the absolute error in this case is going to be defined as 1, right? Right, so that's the absolute error, right? So you subtract the true value and the approximate value and take its absolute value. Now, when you convert a real value that fits into the range of your floating point type, right, then the conversion has an error of 1/2 an ALP at most. So it's 1/2 an ALP. So let's see why that's true. So look, so suppose I try to convert the number 1,000,001, right, to a floating point number, right? So here's my ALP, right? That's what 1 ALP is, right? ALP is the difference between adjacent floating point values, right? So 1 ALP is 10,000. So if I try to convert the number 1,000,001 into this floating point format, then I'm going to get 1,000,000, right? So my error is 1 divided by 10,000. Right? That's the size of an ALP. Now, what happens if I try to convert 1,005,000? Right? Then it either gets converted to this or to this. Right? Exactly how it happens isn't important for our purposes. Right? But what's the difference? So the difference is going to be 5,000. Right? 5,000 divided by 10,000. Well, that's 1/2. So that's where you get your 1/2 ALP from. Now, to compute error in ALPS, right? You this value, but then you convert it to ALPS, right? So how do I do that? So you take your true value x hat, right, and you write it in your floating point format, right? So for our purposes, we'll take x hat, we'll write it with 3 digits in the significand raised to some exponent, right? Times 10 raised to some exponent. Okay? You do the same thing with your approximate value. Okay? But for your approximate value, you use the same exponent that you used for x hat. So you have to make sure that your exponents are the same. Okay? Then you compute the difference. Okay, so let's look at an example. I have 1.29 as my true value. I have 1.25 as my approximate value. Right? What is the error in ALPS? Well, I write that in my floating point format. Right? So what's my floating point format? Well, it's 129 times 10. Now, in this case, it's to the -2, right? So right, you do the same thing with 1.25, right? Components are the same. Right? So what's the difference? Well, that's 4 times 10 to the -2, right? Which is ALPS, right? 1 ALP is 10 to the -2. So the error here is 4 ALPS. Now here's an example where if you were to write this, right? If I was to write out 0.5 in our floating point format, that would be 500 times 10 to the minus 3. Right? Is that right? Yeah, 10 to the minus 3. So when I compute the error here, I write out 12.1 as 121 times 10 to the minus 1. Now when I write out the 0.5, right, I don't worry about the fact that there can't be leading zeros in front of the 5. Right? I want to make sure that the exponents are the same. So that's 5 times 10 to the minus 1. I'll compute the difference, 116, right, times 10 to the minus 1, right? Your ALP is 1 times 10 to the minus 1, right? So that's 116 ALPS, right? Which is quite big. Now, sometimes you've got a true value that you know as a real number, right? So for example, you may know the mathematical value of your true value. So for example, you might have pi, right? You might want to try to compute the number pi using a computer program. Right, so if that's the case, you still do the exact same thing. Right? So you write out the true number using your floating point format, but when you write it out, you keep all of the decimal points that you have. Right? You keep all the digits that you have. So you don't worry about the fact that you only have 3 digits in the significand for the true value. Right? So here I've got a true value that has way more than 3 digits. Right? 3 significant digits. Right? You don't care. You just keep them all. But you have to write it out using the 3 digits in front of the decimal point. 92, blah, 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 times 10 to the 2. Right? You write this number so that it has the same exponent as this. Right? So that's 589 times 10 to the 2. Right? Difference, and you get a difference of 3.875603 ALPS. Right? Now, relative error, if you read the floating point notebook and the error notebook in particular, it'll tell you what relative error is. Right. So for relative error, you take the true value minus the approximate value and then divide by the true value. Take the absolute value of that. Right. When you compute relative error, you don't worry about the floating point format. Right. Using regular math. Okay. So for the relative error, you don't worry about the floating point format. I'm not going to use relative error today. Right. If you want to know about relative error, are we supposed to know this map? Do you mean, can you get an exam question about this? The answer is yes. Absolutely. It's, the syllabus says that this is part of the course learning outcomes. So yes, you do need to know how to do this. Okay, so before I talk about, I'm not going to talk about addition and subtraction today because we are at 19 after the hour. So I'll end the discussion here and pick up the lecture from here on Tuesday. Anybody have any questions about today's content? It's not that hard. I mean, you should have been able to do this in high school, grade school maybe for some of you, or middle school anyway. But this is not that hard. It's just remember that you use 3 digits and multiply by 10 to some exponent. Right? It's really not that hard. Can you go back to the relative error? Yeah. Okay. You have a question about it, Stuart? Oh yeah, of course. So will we be given the values? Vocabulary is new. Yeah, but the definitions are straightforward. Right? Yeah, maybe not grade school. But as soon as you started learning about exponents, you should have been able to do this. Where were you getting the second digit in the approximate second number? I mean, these are just made up, right? All these examples are just made up, right? So, so the question is, where do you get the approximate value? So where do you get the value of x, right? So if you're converting, right? So if you one example of how do you get your value of x is you want to do some calculation with some floating some value of number, right? So for example, I want to do a calculation involving What's a good example in this slide? Well, I mean, so the example I used earlier was I want to do some calculation with the number 1,000,001, right? In this representation, you can't write down 1,000,001, right? You have to get 1,000,000. Are the notebooks meant to be read as? Yes, the notebooks are meant to be read as you go along with the course. Yes, that's listed in the lecture slide page. Do I have it here? Let me pull up onto you and I'll show you. The pacing of the notebooks is a little fast for the beginning part of the course. So if you're not completely up to speed, you don't have to be that concerned about it. So I mean, if you're a week behind, it's not that unusual. A week or even two behind, right? So if you look at the lecture slide page, over here are the notebook readings, right? So according to this, you should be here on the notebooks, right? But again, I don't actually expect you to be here on the notebooks. Right? If you're reading the notebooks, you're probably somewhere in here, somewhere in here. But yeah, you should be trying to keep up with the notebook readings. Any other questions? Vocabulary is new. Will you be given the value? I mean, yeah, of course you're given the values, right? There's no, right? There's no, I mean, if I don't give you the values, all you can write is x hat minus x. So yes, you'll be given values, right? Okay. Any other questions? All right, super. So that's the end of the lecture for today. And I will see you again on Tuesday.